Hi, we are talking about a new experiment called WISPFI, and which is searching for ALPs-Photon conversion on a fiber interferometer. And okay, I'll first talk about the introduction, experimental design, and prototype characterization. And then my colleague Josep will talk about the second part about axion electrodynamic on a dielectric fiber, sensitivity overview, and current test and next steps. Okay, as we know that axion or ALPs can oscillate into photon or vice versa at the presence of magnetic field via the Mach process. We also focus on this E.B term in our experiment. Here is some astroparticle observatory, and we got some good evidence in some parameter space, which shows axion mass in this nano eV range. The more detail can be, you can read the papers from the colleague of our group, and this is a really new one which just online last week. And okay, that's the motivation we want to looking for this parameter space, so we set up this kind of experiment. This is a basic Mach-Zehnder interferometer, and we have a 1550 nanometer laser source. It will be modulated by amplitude or phase, and after that there's a kind of beam splitter, split 50-50 beam splitter, split the beam into the first go to the magnetic field, and of course it goes through the fiber, and the next one will go through a fiber stretcher. To use the fiber stretcher, we can control the fiber length, and so as to get the desired working point for the whole interferometer system. Okay, and then after that, both beams are interfered at this fiber coupler. We got the signal from this detector, and then it will go to a locking amplifier to do some kind of home dyne detection scheme. Then there will be a signal output after demodulate. And also this signal will also send back to the fiber stretcher, goes through some feedback loop called PID, and which is to compensate some noise and also to keep the interferometer in a working point. The probability will be gaγγ BL square, which is similar as the other experiment, and like some later experiment Pivlus, or even the previous talk about light shining through wall. But light shining through wall is gaγγ, the fourth is the second order. Okay, then you can see our total output field is in total with carrier and 2 sideband, which is very important for our readout signal output. And this term is this alpha term is shows the amplitude reduction and also a phase shift via the photon-axion conversion in this B field. And you can see this output power term, which we focus on this one. It will show delta A over A, which is amplitude reduction via photon-axion conversion. And when the interferometer is in a kind of near dark fringe, then we can only extract this signal. Okay, here shows the WISPFI prototype and the sketch of the feedback loop. The main advantage of this experiment is we use fiber, and it can be really long compared with free space laser experiment. And we have a 14 Tesla magnet, maybe it's already shown in the previous talk with WISPFI. We can install the fiber which coiled up in the magnetic field, and the magnet bore is like 12 centimeter diameter. yeah, 12 centimeter diameter. Okay. Yeah, we have two scenarios. The one is we using here shows it's step index fiber. It's normal fiber used for communication, and also we are planning to use this kind of photonic-crystal fiber, which is hollow core in the core. And while using this kind of fiber, we can have a broadband detection because it can be vacuum, or even we can induce some noble gas or change the pressure of the air. And if we only use this step index fiber, then it can be a kind of a resonance case, and we have sensitivity really sensitive to some specific action range. Okay, now I'll talk about the stability of the setup and also some noise contribution. This is the upper one shows the temperature change in our setup. It's a room temperature. And the bottom one is the called PID value change, which is the value sent back to the fiber stretcher to control our setup. And you can see when the room temperature goes up to some value, then the interferometer is not stable anymore because the fiber stretcher has a specific range. If it's over that range, then our lock will be broke. So we will introduce other strategy which were discussed by Josep. And here's the plot shows when the interferometer is locked. You can also see when it's broke, the lock's broke, it will show some this kind of spot. Okay, then when the whole system is locked, we got this spectrum density, which mainly about the noise from the whole system. This line is the short noise level, and we are not yet go to the short noise level, which is our goal in the future. Here, because after the demodulation, the whole system will be in a kind of a DC part, which is in the really low frequency. But it can also do it if we turn off or turn on the magnetic field. But if we want a better signal-to-noise ratio, we can introduce some signal modulation. Now we are planning to do some voice coil actuator to change the position of the fiber core inside of the magnet. Then, because only in the middle part of the magnet is really 14 Tesla magnetic field, but in the different part there will be a kind of sinusoid change. Okay, and so if we have this kind of modulation, then we will see some signal from here. It's a Mach signal. Okay, then my colleague Josep will talk about the axion electrodynamics on fibers and also the sensitivity.
Yeah, thank you, Yikun. So, as Yikun commented, we have a fiber coil that we replace through the bore of the magnet. So first, we want to do some approach to understand the axion electrodynamics on the fiber. So our first approach is based on a classical Lorentz symmetry. For the ones who are not aware of that, this is the presumption of in the axion modified Maxwell equations that the magnetic monopoles exist. So under so the field strength and its dual are invariant under rotation of the SO2 symmetry. And then, so the magnetic and electric sources then are rotated by a certain angle. So, so empirical results. So we know that actually the magnetic monopoles don't exist. So then we have to choose a certain angle for that the magnetic sources are zero. So, and when introducing the axion-like term, as we can observe here, new axion-like terms, axion field proportional terms arise. So if we focus on the linear isotropic media, so in terms of the dB, H, and E fields, the additional terms are marked in blue. after developing and using the Ampere and Faraday laws, and also the Five equation, that is the Axion wave equation. So we can come to a second-order differential equation in cylindrical coordinates, so in terms of the radial and angular directions. And this differential equation, it's in terms of this M. Basically, is the mixing matrix. We can describe it in terms of the photon and action momenta, but also in the non-diagonal terms of the matrix, we have the let's say the coupling and the magnetic field. So our model is to describe or to resemble the geometry of our experiment. It's a bent lab Wi-Fi model. So here we have a system of 3 slabs. So first we have, let's consider the substrate, a core, and then a cladding, but at the end we consider that the refractivity of the cladding and the substrate are basically the same. R is the radius of curvature, and D is the thickness of the slab of the core. And then here in this sketch we consider an infinite slab, so and there is no variation in the y direction, and yeah. So returning to our equation of motion, first we need to let's say our propagation constants of our system depend on the angular direction, but and also the electrical and action fields are basically coupled. So we need first to decouple them, and then by applying some rotation to our propagation basis. And once we do that, we can just solve the Bessel resulting equation that we have, and then solve it in terms of the linear combination of the first and second kind Bessel's functions. And we have the following piecewise system that it's basically decomposed depending on the regions of our refractive index constant, as you can observe here. So once we have solved this piecewise system and known the angular mode number or the modes of propagation for our system and the amplitude coefficients of the before mentioned system, then we can change back to our original basis and basically estimate the electric and action original fields. And then if assuming an action pure beam, we can come and deduce this photon action conversion property formula that basically depends first on this amplitude term depending on the mixing angle. This mixing angle can be estimated from the non-diagonal terms of the diagonalization of that before mentioned mixing matrix. And then the second term basically it's an oscillating term and basically depends on the ratio of the propagation distance in the case of the straight case divided by the oscillation length. Or in the case of the bending case, it's the ratio of the radius of curvature divided by again the oscillation length. So in the case of the fiber, the oscillation length is inverse proportional to the difference of the modes of propagation of the, let's say, rotated fields. And while in the free space, this oscillation length is inverse proportional to the difference of the wave momenta of that rotated field. So to have an estimation on what is the ratio between the oscillation length of the straight and the bending case, here there is a plot that you can observe that for when increasing the radius of curvature, we at the end achieve nearly the unity. But the smaller the radius of curvature is, so this ratio is much higher. So here you can observe the sensitivity of our experiment. So first, here we have for refractive index 1.4, which is, as Jikun commented, it's equivalent to the step index fiber that we are using. We achieve a coupling step of 3.2 10 to minus 11, That's for an axion mass of 0.78 electron volts, and that's accounting for the shot noise, and also assuming that we are in resonance, which means that our axion photon transfer momentum is 0. So, in other words, that the photon and axion moment are equivalent, or the mass. But then we can really go to smaller masses when using a hollow core fiber. So, for example, for 1.003 refractive index, we are in the range of several milli-electron volts. So, and then I will just end by presenting the current testing and the next steps. So, compared to the prototype that you can show, here we pretend to have a long fiber setup in concretely in the arm where the fiber coil will be placed. So basically, we pretend to have where this is the fiber coil through the bore of the magnet, and before that we will have a voice coil basically for moving back and forth the fiber and then trying to modulate the magnetic field. Since our magnetic field is supposed to, it's basically static. And then in the other arm, apart from the fiber stretcher, we have a temperature pack controller just to counterbalance the thermal shift that can occur. So that's a picture of our current test, and in the right you have the magnet that basically it's installed and ready to be integrated in our Mach-Zehnder fiber interferometer. And yeah, as I commented, as the next step, we are currently optimizing our own fiber setup, pushing to the shot noise limit, and hopefully we can implement a squeeze light soon, and then as the next step, replace the step in the fiber by a hollow core photonic-crystal fiber. Yeah, and that would be all. So thank you for your attention.
Why is it a voice coil?
Yeah, sorry.
Why is it a voice coil? That's my first question. The second, it seems like you can do all types of experiments, light shining through the wall, helioscope, and helioscope with this technique, right?
Well, so that's not really it's not light shining to the wall. So, well, first going to the voice coil is just basically a device that shakes the fiber and pretends to move back and forth the fiber that will be placed through the bore of the magnet, and then pretend to in that sense to because at the center of the bore of the magnet we should have 14 Teslas, but this is not this is just at the center, let's say, and then by shaking that a few millimeters, you can really change the magnetic field. And yeah, and then returning to the. Oh, you want to comment that maybe? The election too?
Maybe, but for, as you mentioned, the helioscope or election to us, our setup is kind of like the production part of the election to is like the left part of that. So I don't think it can be a helioscope or helioscope. It's only related to detect the protection conversion and some energy loss and also phase shift.
One more quick question.
Very short. Is the assumption of an isotropic medium in the quasi-hollow core fiber justified?
So can you say it again, please?
So you have this fiber which is nearly empty, which has lots of little channels, and is the assumption of an isotropic medium justified in this case, electromagnetically? discuss it later.
Okay.
Yeah.
Great. No, we have one more time. Okay, thank you very much.